This is the summary presentation for the class of Structures and Properties of Material with the topic of creep phenomena and heat-resisting alloys. The topics that are covered in this presentation are creep phenomena, creep mechanisms including power law, Naburro-Herring, and Coble, Larsen-Miller parameter, and heat-resisting alloy microstructures. Most of the explanations here are based on Callister's 9th edition of Material Science and Engineering, as well as some internet websites. To begin with, we will define the term creep. Creep is a phenomenon during which a permanent deformation of materials happens when subjected to a constant load or stress. Creep often plays as the limiting factor in the lifetime of a material. It is not limited to metals only, but it also applies to other materials, such as polymers. This graph depicts the behavior of creep on metals. There are three main phases in this deformation. It starts with an elastic instantaneous deformation when some constant load is given, shown as the immediate jump on the y-axis. The first phase is called the primary creep, also called as transient. The characteristic of this stage is its decreasing slope as time goes by. Physically, it shows that the material does not deform easily. The next phase is the secondary creep or the steady-state creep. As its name describes, this phase has a linear slope, during which the material deforms steadily. The last phase is the tertiary phase, which ends with rupture. As can be seen from the graph, the increasing slope signifies that there is rapid deformation, which leads to rupture, such as grain boundary separation, cracks, or even cavities. The impact of stress and temperature on creep behavior can be seen from this graph. There are a few things to be observed as the temperature or the stress applied increases. The instantaneous deformation or the jump increases when the load is given. Note that this affects metals at temperatures greater than 0.4 times its melting temperature Dm. Also, the slope of the graph increases, which means that the rate of creep strain increases. With this, the lifetime of the material also decreases since the material came to a rupture more quickly. The relationship between the rate of shearing and stress is described by the first equation, with K1 and N as material constants. The second equation shows the relationship between the rate of shearing and temperature, with Qc as the activation energy for creep. For both Coble and Nabarro-Herring creep, the value of N is 1, whereas for the power law creep, the value ranges between 3 to 10. Creep results in changes in the material's microstructures, and it is categorized into diffusion and dislocation, which will be explained in this presentation. These can be further observed through power law creep, Nabarro-Herring creep, and Coble creep. The power law creep, also called as dislocation creep, is a creep mechanism that causes deformation to happen due to a high stress at a high temperature. Microscopically, the dislocation that occurs here consists of two motions, glide and climb. This combination of glide and climb allows the dislocation across a crystal lattice to happen a lot easier than simply a gliding motion. The strain rate due to dislocation creep is related to stress and temperature using this equation, where sigma is the stress given, d with the subscript is the efficient diffusion constant, g is the shear modulus, b is the Burgers vector, and k is Boltzmann constant. The power n is usually between 3 to 10 for this mechanism. Whereas the previous mechanism is done by dislocation motion, this mechanism, as well as the next, will be done by diffusion. Nabarro-Herring creep happens at a high temperature but a low given stress. So when a tensile stress is applied to the grain in the vertical direction, the upper and lower parts are in tension, while the right and left sides of the grain will be in compression. The parts of the grain in tension will have vacancies as the stress is applied. The vacancies from the upper and lower parts move across the grains to the sides, while the atoms move from the sides across the grain to the upper and lower parts. As a result, deformation happens and the grain is elongated due to diffusion. Note that the strain rate is inversely proportional to the square of the grain size g. Coal creep is a mechanism in which the material deforms due to diffusion. The main idea is that at a given low stress and at low temperatures, deformation happens in the atomic scale. Similar to the Nabarro-Herring mechanism, stress is applied in the vertical direction, causing the upper and lower parts of the grain to be in tension and the right and left sides in compression. In this mechanism, however, the atoms diffuse along the grain boundaries instead of across the grain. This still results in the elongation of the grain. A notable difference from the Nabarro-Herring creep in the equation of the strain rate is the power of the grain size g. Here it is to the power of 3, whereas in the Nabarro-Herring creep it is to the second power, and this indicates a stronger dependence on the grain size. Sometimes, however, data for creep phenomena cannot be obtained through laboratory experiments. The Larson-Miller parameter serves as a solution to this problem. Basically, it allows the extrapolation of values using data obtained from creep tests done at higher temperatures for a shorter range of time than the normal tests. So the Larson-Miller parameter m is equal to T, the temperature in Kelvin, times C, a constant, plus the log of T sub r, which is the rupture lifetime in hours. There are factors that contribute to creep behaviors of metals. Microstructure-wise, at high temperatures, larger grain sizes result in creep resistance. As what happens in cobalt creep, it is easy for vacancies to move along the grain boundaries. However, with larger grain sizes, there is less grain boundaries, thus resulting in difficulties to form. Superalloys are already creep resilient, and it can be improved by directional solidification that results in elongated grains or single crystals. These single crystals are resistant towards creep since they do not have grain boundaries. These are the references used in making this summary. Thank you.